after all a little bit of diversion after all the graphics talks in the past few days. It was an audio extension to the X-Window system, and in case you're wondering why I'm using a microphone, I'm just doing a live demonstration of the system just to show that it's real and not vaporware, because everyone likes live demos. First note where this all came from and why I'm using this slide decoration. It stems from a research project originally done at my employer, but I'm plugging this out now about this research project and trying to make this into something useful otherwise, because well, code written to the paper is something different from code written that's actually useful. Okay, what's running here currently is this small application I wrote. It's capturing my voice through this microphone. I'm playing back through loudspeakers. Yes, it uses, of course, the only extension and what I can, for example, do is activate a few effect filters. I don't think I need to explain this too much. Okay, this is fairly audible. It's a low pass filter, and well, not much left of my voice after that. Let me turn this back on. What I also can do is, for example, desktop audio mixing. So if I just start a second audio application, pick this one. Well, okay, so you can hear my voice still, it's all mixed together. And oops, the mix sound is done by this small application that I put in my tray. It's the audio manager. It performs a similar role to the window manager. It determines how multiple clients concurrently accessing the audio device are multiplexed onto the output. It can do a number of effects as well. For per client volume settings, this is quite easy, or it can shut off clients completely, or just kill this. I can do other fun effects. This is on the playback application I'm talking to right now. So, well, this is better audible if you sit close to the speakers, so my voice should be there. I guess I'm mixed up the left and right settings. That's just reversed here on the overhead relative to my desktop screen. So, but I think I will just discard the microphone for now, because I actually prefer strolling around while we're talking a little bit. Okay, so now this is extension. What you would probably expect, what I would like to note first is that audio processing is performed only inside the X server, so the sample data is not passed back from the X server to the client application doing effect processing, and not passed back to the audio manager doing the multiplexing and mix down to the final audio device. It's processed under control of the client, but inside the X server. For obvious reasons, I do not want to introduce any latency by passing sample data around, but I want to process them inside the X server. What you probably expect is that I'm building some sort of filter graph or filter chain, because this is what basically every other audio system does. I'm not doing that because filter graph approaches tend to lead to a plug-in inflation. You just have to keep adding more plug-ins, and it never ends. And of course, I don't want a whole lot of plug-ins into the X server. I hope no one does. And I've done something much more simple, and I will explain that on the following slides. So, first of all, I've written not only one X extension, but these are two X extensions that are active here at the moment. First one I call time, the other one I call audio. I could have implemented this as a single extension. Of course, I did not just do for the sake of presenting the clarity of concept, that these are really distinct concepts. The time extension could have logical overlap with the sync extension. If you don't know what that is, don't care. It's not one of the most important X extensions in existence. I use this to provide time services for audio processing and playback. The audio extension does all of the run audio work, including playback capture and this processing that I demonstrated. So first, let's give a short overview of what I need of this time extension for my timing purposes. This extension introduces two new server-side classes, two new server-side objects, clocks and schedulers. Well, clocks are
well, what you would intuitively expect the job to be is provide sample information, you can start and stop with queries, it runs independent from any client that provides ticks or something. And the second, more interesting concept is that of a client as scheduler. Scheduler is always attached to a clock, or one or more scheduler, no, zero or more schedulers are attached to a clock. And it permits the client to submit operations to a scheduler which, unlike normal X requests, are not executed immediately, but they are deferred to a later point in time. And it submits timestamps that define when or when not these operations should be executed. It's primarily timestamps because they want to have operations expired after the time the service overloaded and simply just can't handle the request. It should be permitted to drop things. The operations that I can perform through a scheduler is sample processing. I'll return to that. But not only that, actually I can also do some render operations. Render operations pertaining to render extension. We could also add other operations, but these are the most interesting. I don't need them for all. I'm just mentioning them because they are in the implementation, and I need them for other work, for video work that I've also created. But I don't want to talk about that, just mention that this concept is of course very generic and you could do more than that, more than just this concept. Okay, the audio extension also includes a number of new server-side resource classes. The first is a sample buffer, which, as the name suggests, stores sample data inside the server. It's a one-dimensional data structure, so pixels store pixels, the sample buffer store samples. It's one-dimensional, so accesses to a single index value, and it stores sample values for each index value or for limited range of index value. The values stored are scalar. This means if you want to do multi-channel audio or stereo audio, you need two sample buffers, one providing data for the left channel, one providing data for the right channel. I've done this decomposition because it greatly simplifies the application programming interface, and well, otherwise it wouldn't have these quite clutters. I tried this in the beginning and ended up simplifying it this way. The sample buffer really only store sample values, but there's no temporal dimension of each sample. This means they do not store any sample rate or something. So the server just stores samples without knowing according to which sample rate they should be processed. This is added later using a different mechanism. I'm just mentioning it here. Return to this later. The extension supports several mechanisms to get data into and out of sample buffers. Of course, you can upload, download samples simply through the X protocol, much like you can upload pixels. Some elementary functions in these, and arithmetic functions. These are really simple functions which I try to illustrate here a little bit. For this example, multiply, accumulate. You just pick a range of samples from one sample buffer, a range of samples from another sample buffer. These are multiplied pairwise, and then plate or accumulate it into a third target sample buffer. So all these arithmetic operations are of a similar quality and like the operation I just showed on the right. So they are really simple, the operations you can perform through the audio extension. Another type of operation I can perform is a convolution operator, which of course allows me to implement finite and fast response filters. This convolution operator is a little bit more generic than what you would find in textbooks on digital signal processing. It's a little bit generalized discrete convolution operator. And this convolution operator is also used for resampling. I already said a sample buffer does not store any associated sample rates, so a client has to keep track whether the samples in a given sample buffer have to be interpreted as 20 kilohertz or 44 kilohertz. The server doesn't care, it doesn't know. So if the client wants to transfer sample data from one buffer that the client knows is to be interpreted at 20 kilohertz into a sample buffer that the client knows is to be interpreted at 48 kilohertz, it explicitly has to issue a request to transfer the data and do resampling at the same time. And this is usually done using convolution filters. So the server also never does any implicit sample rate conversion. This is also deliberate in the design because unlike for images where you can use, for example, bilinear interpolation as a safe default that gives good results, there is no such safe default for audio that you could really use. It very much depends on the application scenario. So I decided to pull it out of the server and provide it that, well, the client just had to do this and had to issue according to the request. The sample buffers can be used as static sample buffers in that they store sample values for static range of indexes, but they also support a sliding window concept for streaming audio. Well, try to illustrate the concept here a bit better, I hope, than with words alone. What I can do is, if a sample buffer represents sample values for index values B0 through 7, then I can change the window of interest of the sample buffer to, let's say, 4 through 11. And as a result, these sample values, they drop out of the window and their values are lost. And a number of other samples, they are shifted into the window, they are initialized to 0, but you later load, you can later go and place other values into the sample buffer, and probably you should, using the mechanism on the previous slide. You can always extend all the bounds of the sample buffer. It has well-defined semantics. It's basically the same as if you would draw outside of a fixed map or something. The data is simply lost, or if you read back there, you just with these fragments. It's well-defined and it's always possible. This sliding window concept, or this window shifting concept, I will introduce that for several reasons. First of all, the sample buffer concept allows random access to any position in the sample buffer at any time, so I'm not using simple FIFO buffers. This is important for loss and recovery of synchronicity. And this sliding window concept provides a good decoupling between producers and consumers of sample data. Of course, the roles between producer and consumer that may change. Sometimes the client, the producer, and the server, the consumer, or the other way around, depending on if you're capturing or playing back. And this allows me decoupling of that. Note that access within this range that is unaffected by the shift, so this overlapping range of all the new window, access is always safe. And so if anyone does control access in this range, nothing happens to him. So you're always safe if you shift the window at a rate and make sure that all accesses of all concurrent accesses fall into this overlapping range, you're safe. Clients may have this window shift operation has to be performed by clients. The server does this not automatically. It's a client request that the client can perform on a sample buffer. And well, there are multiple options. Of course, the client may have to use this and make sure that the window is always played correctly. You can do a large window with multiple, with infrequent lazy shift, or small window with aggressive updates. It all depends on the client and the synchronization requirements. So the server simply does it here. So now that we can do, that we can store and process or compose sample values inside the server, we probably want to do something else with them, and that is probably playback and capture. This is achieved through two other server-side objects. The first is a Pcm device. Well, it should be quite obvious what this is, something that's capable of capturing or playing back Pcm data. And the second is a Pcm Context. This is essentially a configuration of a Pcm device, so a set of parameters that can be applied to such a Pcm device. It contains information such as sample rate, may contain other information such as allowable playback latency and other things. And it also references, typically references one or more sample buffers, and points to position inside these sample buffers, which serve as the point where playback or capture begins. And once this context is activated, it will just start reading or writing values into the sample buffers beginning from this position. Note the client has to do window shifts to make sure that capture and playback never slides out of this window. Otherwise, he will go to this grayed out area and read back zeros, which equals silence in the case you lost synchronicity. The important connection point to the time extension to the timing services at the beginning is that each Pcm context can also serve as a time source for all scheduling operations. So this means I can attach a scheduler to such a Pcm context, submit operations to the scheduler, and these operations executed synchronous to playback capture of sample data through a Pcm device. And of course, this is what the client application that I demonstrated at the beginning actually does. It just submits request to such a scheduler and realizes the effect in this way. For example, for the reverb effect, I just added multiple copies of multiple small echoes behind the main final using multiply accumulate. This is very easy to do, and finally the pulse response filter for the low pass filter is also quite easy to do. The implementation tries very hard to satisfy all of this, all these timing requests. Actually, it usually executes most of the client's requests in a dedicated real-time thread to make sure the timing requirements are really met. Also return to this. So, now just a few words on the desktop audio mixing model. The way it works is roughly shown in this figure. The audio manager goes and sets up playback through a Pcm device from a sample buffer created by the audio manager, or multiple sample buffers created by the audio manager if you want to use stereo audio, obviously. And all the other audio clients that want to playback something, they also create their own sample buffers in which they provide the data they would actually like to playback. But instead of letting the Pcm device read from all of these sample buffers, the audio manager's responsibility to issue composing operations that transfer the sample data from these slave client sample buffers into the main playback sample buffer. And of course, this model offers a lot of flexibility because the audio manager can basically do what he wants with the sample data. It can simply ignore a client, in that case, use it, or it can, well, do, for example, positional audio as I demonstrated at the beginning by, well, attenuating or left and right channel accordingly. A lot of options. Something that I did not demonstrate, but that is certainly also possible, is transparent device switching. If I just attach another audio device and add it to the user, instruct the audio manager, okay, now don't playback from the first audio device, but choose the second. It can just pull this Pcm device under the client, but start playback through the other audio device, so the client won't even notice. And the nice thing is, this requires actually no cooperation from the server. All the server doesn't know or doesn't care that we just switched the main playback device. The audio manager can do this completely on itself, provided it learns that the new device has appeared, something like that. Okay, now a few rather random implementation notes on how this looks in the inside. The extension itself is really tiny. It's about 8,000 lines of pseudo code, 8,200 or something, and this report includes all of that I've just presented. This also includes the ability to send timed render requests, so if you factor that out, you're well under 8,000 lines of code. I tried very hard to implement it without any intrusion into the core X architecture. Just simply to make it easier for anyone who wants to deploy it for testing purposes. You can basically just compile it, download it, load it dynamically, but there's one caveat. You need to press save X server because I just have to start a dedicated audio processing thread and usually with real-time priorities, otherwise it simply can't meet useful timing requirements. So you just have to relink the server against the thread space libc. Although on Linux systems you can do a neat LD preload trick, so if you LD preload to the correct thread library, it will also work. Yes. Otherwise, I'm actually not really touching core code, and I'm not really touching the threading model of the X server. The dedicated audio thread really only does audio processing and nothing else. The drawings not influenced from this separate thread. This bounce back to the main X thread if the need ever arises. About these real-time audio effects, I also mentioned that the server tries very hard to execute client requests in the time frame specified by the client. This usually means that the client operations are executed in the thread performed with real-time priorities. So this opens the window for clients to execute code in a limited way in real-time thread. Of course, I need a little bit of access control for that. First, of course, to provide fairness, and also to prevent the client from locking up the service completely. We don't want a process that doesn't have capability to run real-time to use this mechanism to lock up the machine. And the approach that I've chosen here is that I approximate the cost of the requests that are executed or that would have to be executed, and according to this cost model, schedule them into real-time thread or deny scheduling them into real-time thread or maybe dropping them. This is very easily possible in this case because remember the operations that I'm doing are really simple. They are always on the scale of multiply accumulate. So do a fixed set of multiplications, do a fixed set of addition. You can actually compute the number of instructions you need to do this very precisely, and you can actually also compute the number of cycles you're going to spend, even if it blows your cache completely because it's just not in there. You can compute that fairly accurately. I've done a lot of experiments with that. And it doesn't hurt if you overestimate. I'm probably overestimating in a typical case by a factor of 2. This doesn't matter because it just means, well, if you overestimate by a factor of 2, this only means that you can only get 50% of CPU processing time ever spent in the real-time thread. You don't want to spend 100% of CPU processing time in there anyway, so overestimating really doesn't hurt that much in this case. You really want to listen to the low 10 to 20% anyway for just to defend against intentional or unintentional overload cases. So, to sum it up, I think this approach to integrating audio into the first idea it just means a lot of the existing infrastructure. If you write standalone audio, then you actually end up re-implementing all of this. And you also have to suddenly have to implement a security model. For example, if you go into the Explorer and just enable X8 or something, then you get security, of course, for the extension automatically for free, so you don't have to worry about that. And what you also get on the video synchronization, if you want to do that, is essentially free. You just schedule stability operations on the big screen with the audio, and it works, and it also works reliably across the network. I tried to make the audio model mimic the existing X image and video processing model quite closely. The similarities are of course intentional. Try to maintain no quality in the server and shift more complexity to the client, but they should not neglect to tell you that the client can in fact get very complex because you have to do a lot of planning ahead, and maybe if you decide, okay, this is not valid anymore, I want to do something different, change your mind, roll back to do something different. And well, I can get low latency through this mechanism. This is quite suitable for desktop audio setting. I can place, for example, sample buffers into shared memory, and in that case, since the sample buffers or the data container is only pulled by the real-time threads running inside the X server, you get essentially the same latency as, for example, Alpha-Emix or any other custom that uses shared memory to communicate with the real-time threads. So it's quite usable. We have some graphics drivers. Ironically, it's exactly the graphics driver in the laptop that's preventing me from achieving the latency that I actually desired. So, this is a little cool. Maybe I pick your curiosity if that's the case. You can try it out. It's all there. The sources are all there, and I intend to put in the mailing list. I have not done this yet, but I will do it Monday night at late. So otherwise, if there are any questions, I'm here for interrogation. I don't know if we may still have a little bit of time for that. Just a few minutes. And otherwise, I would just thank you for your attention.